never been to a rock wall in my entire life, unless I'm doing it while I'm sleeping or something.
I sent you
like a
the
stretch
live
of
stream
moves.
link in your messages.
Let's see if it works.
Why don't we like do a Discord stream?
That's probably our last resort, if we can help it.
I think that is last resort, yeah. The whole thing is that we need like potential alumni.
Okay,
and,
well,
like there was that Blue Origin guy who watched our YouTube video.
well, it's on.
Oh, did he actually watch it?
Yeah.
Shoot.
Yeah, and he said
It's
it wasn't
on
great.
and it's working fine.
Okay.
Now, can you? It looks right. The orientation's right.
Yeah, I switched it to. You have to set the horizontal position.
Okay,
at the
well,
very
then we
beginning.
should be fine. We just gotta send that link out.
Yeah. Could you do that?
Do you want a chair like in the middle?
Yeah. What should we do?
That might be an accessibility.
You want to hold it? You want to be cameraman the whole time?
Dude, I'm just gonna be sitting here just like
Oh,
Dude,
shit.
like worst
Oh, shit,
cameraman
storms on the
possible.
door.
Oh, OSHA. That's for construction.
FBI OSHA comes in.
What?
He
Oh, you
said it's
could.
an
How about the desk?
accessibility
How bad would
concern
it be on the
after
desk?
chair. He's like, I don't care. As I push his door thing.
I wish it had rubber
Send
feet.
out the link on Discord or.
Yeah.
That's not bad. That's good.
This is good enough.
Want to be cameraman? Thanks.
I guess I am now.
Look and show
Oh, he's
it.
dealing. He's the one that's dealing with it.
So do I just keep this here?
Yeah.
Okay. I'll make sure to like turn it around towards me to get reactions and stuff like that.
Okay. Yeah.
Just
Brandon, do you want me to send the link out on Discord?
Do both. I don't know about. I feel bad. I've sent like 4 emails already.
It's probably best to email it because it's just gonna reach the most people.
Yeah.
I can do Discord too. I can just.
Yeah, throw it
Discord's
in there.
good.
Especially if it's like the CSU team. They tried to share theirs. They're probably not on the email list.
we need to put this behind while he's doing that the entire presentation.
Man spread it to the max.
Put the camera between your legs and it's just thigh on each
There's
side.
a pure little
Shit.
rumble going on, and it's just me just evacuating myself.
Karen, we are live. I hope you know that.
Oh, we are?
We
Yes.
There's nobody on it.
What?
There's nobody on it
I
right
know,
now.
but
It'll be
they can rewind it.
Is there audio? You should mute that until we get done.
guys are.
I think it's on.
So I get into some program where basically
Brad, is the microphone on the
that
phone?
you want. Okay, I want output.
No, if the mic is on, is it the phone or is there a mic somewhere else?
I think it's just like.
Okay.
Audio might not be.
I'm coming.
Depending on the situation.
Can you pull up your live stream and check what the audio level's like?
The most significant thing.
Thank you.
Say it's unmuted now.
It's muted now?
No, it's unmuted now.
So
We can hear now.
Now, when my boss
Live
wants to
stream
push
is
a
live.
release today,
And depending on
Or
what switch.
Don't say anything stupid.
but
We'll be starting in a few minutes.
I know who I am.
but yeah, I know because you're probably thinking to yourself like push a release on Friday is really dumb.
Yeah.
Like if there's issues that you're like coding, but like
They bought.
I don't know. Either way, he wants to do it, and he needs me to like make some changes and put them all into the code and stuff like that.
And they're like, well, you know, this program.
All right.
But they bought, which had slightly different pinning.
You should get into magic if you ever wanted to, or
Genuinely
with
curious.
a small group of robotics people who are playing magic, and I have decks you can borrow.
Yes?
I open it.
There's the supplemental
There's a
document.
PDF in the OneDrive that you can open up. That's like the first one. That like has more details.
All 46 pages?
Yeah, I might.
What?
Thank you for looking at it. What's
This?
your name again?
Do you know React at all?
Okay. No, okay.
You know JavaScript?
I think
Yeah, you probably won't like understand any of it. But
I have chemistry
I know.
every single
I'm very
evening. And you put anything, it's
It's even more time.
that makes sense, but it's a
Nice-
lot.
nice view of yellow.
Like, it's a lot to like explain to someone in one go. Like, if you ever interested in me like teaching you like not enough that, then I definitely could. Yeah. But like yeah, like so you know, it's like a lot more like coding than I do, you know. It's very different. Do you know how to read this at all?
The best part about Compass is
Yeah, this is printing text. This is like a div, if you know what that is, just like a box pretty much. This is like a button that has an icon in it. Yeah, yeah. Okay. But this is for mobile.
Oh, I got you and the screen in it.
Besides that, yep, that's what I'm working. Well,
He is, but
my boss
he'll
just
lean back.
texted me today asking me to move some pieces to, like, so I gotta-
True, you could.
I gotta
That's
do
up
that
to you.
RQ.
I mean, like that, he's fine. It's just when he's like leaned forward.
I'll just sit back.
All right.
I forgot about that. My bad.
You're good. You're good.
Well, you probably you know what you mean.
We do.
Just the stuff I did. Yeah, I thought so.
Smile.
You know the least so like whoever gets me to whatever he says is the inverse of what it's actually.
Yeah. One of these days, it's just gonna crack and not go back into place. I'm gonna feel something like a disc just go. Well, that too. My neck hurt, but I won't feel anything else.
I figured I would go over the flow charts for the PCD, but outside of that, I didn't really know.
Did you just meow? Yeah.
You know what?
I know, I just didn't want to be. Okay, yeah. I mean, yeah, I know pretty much all this stuff. I expected everything that I would be sent here already know, so I have to prepare.
Shane.
What's he
doing?
If anyone else came in, make sure you swipe in.
Is he doing?
No, we got pizza. Yeah, you'll figure it out.
It is around
Really?
3.
Did you know? That's pretty cool. Shane's an awesome guy. What's up? When did you join robotics? Just tolerate it. When did you join robotics?
Like last year.
Leave over.
Dude, I'm there all the time.
I'm fine. I'm fine seeing
You want me to move my shit really quick? Yeah.
Like grabbing it.
Dude, how's it going? You're still edging it this year, right? Edging your toes.
That was not.
You're like edging, living at living at edge. Yeah. Dude, your roommate named Joe, right?
It's time to start.
Hey. Oh, yeah, you are.
That's true.
Oh yeah, Jacob. I'm gonna play some Magic with Garen after this. I'll play one game and then I'll be done. If you're free, are you free?
Thank you all. Thanks
Not
for
really.
coming.
I was going.
I'll just start off here.
One game?
Yeah, this
That's
is
all right, no.
preliminary design review.
Don't-
And first, we're gonna do introductions. I hope everyone got pizza. We can still get pizza now if anyone missed it, because we're kind of just slowly going into it. But to start off, I'm Brandon McHugh. I'm one of the project managers for the team, and I've done a lot of work to make this slideshow and the supplemental document, a whole lot of documentation, and then I just help wherever I can with mechanical or whatever. But yeah, that's basically me.
I'm Aiden, I'm the other project manager. I also help Brandon with a lot of the supplemental document and presentation. And I mainly work with electrical and software, but I'm versatile and I work where I can. Do you want to do the managers next?
Nathan, other officer.
What's it?
Yeah.
Oh, yeah. I'm Nathan. I'm vice president. So.
Okay, John.
Sorry.
I'm Jonathan, the treasurer.
Yeah, we can do Nate.
I'm Nick. I'm the mechanical manager.
Eli, the electrical manager.
Jackson, I'm the software manager.
We'll hear from these guys a whole lot more throughout the presentation. We've got our 2 wonderful advisors here. We got Sam Estramateur and Nice Fight Master. And we got an
Alumni, Lucas.
What years were you on the team?
I was on the team 2019 to 2023, and I was project manager and then the president for a couple of years.
Thank you guys for showing up. Got a lot of good members here. It means a lot. If you show up to all the design reviews, then you are eligible to go to competition with us in May. Yeah, we can start going through. Yeah, but I'll just reiterate about the competition. Yeah. Okay, we already did the org chart. Lane is not here, unfortunately, but Lane is watching. So.
Hi, Lane.
Hello, Lane.
Love you.
Check. He's the president. He does a whole lot. He literally signs us up for competition and helps with a bunch of the documentation, communicating with like sponsors and stuff like that. And yeah, we've also got. We can do introductions. Liam
I'm Liam. I'm the electrical power sub team lead.
and Garen.
I'm Garen. I'm the PCB lead.
We don't have John Roth here, but here's the software lead. And we've got Zach couldn't come today either. He has to work. But final mechanical lead, John Double Dips over here.
Also the locomotion lead.
Man of many hats.
So basically, I mean, most of you guys should know, especially if you read the supplemental document or the guidebook. But anyway, I'll just reiterate. Here's my quick 3 bullet points for what is competition. We have to design, build, and operate a lightweight, power efficient, preferably autonomous lunar rover that can dig as much regolith as possible from the excavation zone, drive across the obstacle zone, and dump regolith to construct a berm in the construction zone. The berm is basically just a pile that's over here in this corner. Start here, drive around. They don't usually like us going through this area, but I don't know, there's a couple little nuances about the arena itself. And yeah, we do two 15-minute runs at UCF, which is the University of Central Florida. And if we place top 10 at UCF, then we move on to the NASA Kennedy Space Center. And each of those runs are 30 minutes long. So we like to plan on a robot working for 30 minutes, and we would like to plan that we will be in Florida for the full, like 10 days or whatever. So there's a whole lot of budgeting and stuff that goes into that. Next we can go into, we have a video of Melody from last year. It's also just Lane and John. You can see we got those old wheels on it. I'm sure all of you have seen Melody around Express. And this design is fully like a pure front loader. It's got articulation for the overall like big angle of the control arms, and then articulation at the bucket. Yeah. We did pretty well. We actually got second place at UCF out of the 35 teams that were competing, and then we moved on to top 10 and got stuck at one point, but we still managed to get seventh place. We were pretty happy. I think Alex took this wonderful video, so thank you, Alex. And here's our schedule. So basically, we like to say that we start May 30th, which is just like a week after competition. And some of you, especially on the live stream, people might be wondering, like, why is this the preliminary design review? A lot of other teams will start with the system requirements review. The past few years, we've done a public system requirements review where we have everyone giving external feedback. But this year, we were going back and forth about how we can expedite our design process, make everything a lot sooner. Originally, we wanted to have the system requirements review like in May, but we ended up doing something more of a concept status session. And then the SRR we did right after the guidebook was released. And we didn't have enough time to do like a very formal presentation off of the new guidebook rules. So we mostly did it internal, just the leadership. And then we sent information out to the advisors. We got a couple things from you guys. And basically we proceeded from there. We set our requirements throughout the summer, and just in that SRR meeting immediately after the guidebook was released. And we went through, we did the budget presentation. We did pretty well with that. We were actually awarded how much money?
From the school, we were awarded. What was the question?
How much money from the school were you awarded at the budget presentation?
We were awarded 7,500.
7,500. So that's great. Yeah, so that's good. But that's all we need, and we'll be able to go to the competition and everything as long as we build the robot well. So now this is the PDR, the preliminary design review. This is where we will iterate all of the concepts, the preliminary schematics based on requirements we've already set. We'll go through basically where we are at this point, which is before major design, before critical design starts. So we also submitted the project management plan, realized those dates are flipped. And critical design review is the next one. We're thinking about doing that right before Thanksgiving break. If you guys can come to that, that'd be great. And we got other things after that, but those are the big ones. System verification review, that'll be sometime in March. So, yeah, any questions about the schedule?
I don't want to spend the most time on this, but the top graph is our presented values that we did to the school, and just general budget expenses throughout the year. Yeah, and then this bottom table is a table we will review at each of these critical design reviews. just as a good way to track expenses and where our current status is at for the expenses of the team. Something I don't have on here, this upcoming week, we will start collecting dues more officially. I'll send an announcement sometime this weekend. So come Monday, either me or any of the officers, you can pay your dues and they'll get you a shirt. Just make sure they know that you paid. Don't want anybody paying twice. So yeah. Any questions? Great.
So one major change, this is like a huge point to discuss at the SRR, is the change to the arena. And at first glance, also at a longer glance, because the pictures aren't great resolution, but basically they switched the obstacle zone with the excavation zone. So this is, we have, this one is last year's, actually. Anyway, but basically the robot would start here in the starting corner, go up through the obstacle zone, and then immediately dig in the excavation zone, drive forward, dump. And you saw that in the video. And we would just reverse, dig again, dump, just this straight back and forth linear line, and somewhere between like 25, these are in centimeters, so it's like 2.5 meters or 40 centimeters, 2.5 meters or 4 meters, you'd go back and forth. That's the whole driving distance that we had to do last year. This year, they have the obstacle zone separating the construction zone and the starting area. Yeah, separating the construction zone with the excavation zone is the really important part. So you'll start here, dig, and then have to navigate through the obstacle zone and dump in the construction zone. And we want to do multiple dig cycles. Like we have 30 minutes, we have time to do, I don't know, upwards of 20 or 30 cycles. Especially with the old one, we would have that much time, but now you have to do basically, yeah, like 3 times the amount of travel distance. This is the big thing. This is why we had to change a lot of designs going forward, and we'll talk about those. But yeah, just note this as a major change. So yeah, this is the big decision. This is basically, do we continue with the pure front loader of Melody? Do we keep trying to just make that faster and make that more efficient? Or is it more worthwhile to implement a storage deposition system? If we have a storage system, then we could do multiple digs, store it, and then go through the obstacle zone, and then dump it all at once. Whereas with a front loader, where it's just loading on the front, depositing off the front, you can only hold what's in that front bucket. And we had this whole analysis. It's more broken down in the supplemental document, but here are the key points. We have Melody's scores for each of these categories. We achieved a burn volume of 75,000 cubic centimeters. All these other inputs like the weight and energy, and you can also note the dig cycle distance. That's the big change. And for us to, yeah, like 75,000 cubic centimeters, that was 7th place, which is great, but we want to do better than that. So for us to get first place, we'd have to do 136 cubic centimeters or 170,000 cubic centimeters. The whole scoring depends on construction volume as well as weight of the robot as well as power usage. So that's why some of these numbers are different. It makes a little more sense in the supplemental. There's more detail, and Eli's put together a really great table for it. He should also explain some of it. Do you have any?
Yeah, the regular storage cap for depositees, we estimated 15,000, not 1,500.
Basically, we wanted, no, some of these numbers got messed around. We wanted Melody 2.0 to have 5,000 cubic centimeters for our storage capacity. We were thinking best case, we could almost double what Melody did. But for depositee, wanted to like 6 times that. So we wanted to hold 3 bucket amounts of the new bucket. And that, like raising that number allows us to raise the number of kilograms that we can have across the system. And then greatly reduce like the speed we would have to drive at. This was like one of the main factors that had us decide on implementing a deposition system. Like really we would have to, we kept Melody, we kept the front loader design, we would have to drive significantly faster. Just because you have to go over so much more distance. But if we did a deposition system, then it's like pretty much the same. And it seems pretty doable. Any questions about that? I didn't explain the best, but does that make sense? We have had some experience in the past doing a deposition system. I think we have a picture of Spacey on here somewhere where it was basically like using this type of bucket, which hinges around the top. You scoop and then deposit all the way into a back storage thing. And it's like a garbage truck kind of, so like you do little scoops and then like the whole back will flip back. That's kind of what we're working on. Yeah.
Oh, remind me, that the regular storage cap for depositing, that's for the total volume of the deposition system?
Yeah.
Right, okay.
Yeah.
We'll multiply that number by 10.
Yeah.
Yeah.
So that makes more sense.
Yeah, we did these edits like last night. So this is a new slide. We should have done a little sooner. I don't know. Trying to make things a little more organized, but oh well. So yeah, I think that makes sense. Go to the next one. Were you gonna explain?
Yeah.
Okay.
So we're just gonna briefly go through the internal and external requirements that we set at the SR just to get everyone on the same page. Basically, we took the numbers from the trade study we did with the deposit system versus the front loader, and we kind of set those numbers as our goals for each subsystem. So yeah, we have, for the system, we have a max mass of 50 kilograms that we're trying to shoot for. We're also trying to hit a total dig volume per run of 172,000, and they're also trying to dust proof as well. That's just normal requirements. And obviously, you go down the list where we budgeted out what subsystem will have what weight, and we're trying to shoot for. And all these will have technical performance measures, which were detailed in the supplemental document. Any questions about this slide? Anything to add?
This is just a question. You have like at the very bottom bandwidth usage of 2. What did we have last year?
Okay, when did you guys add this slide?
This has been in for a while.
It's been here for a minute.
Okay, gotcha.
Last year, I think out cameras, we were something like 500 bytes per second. And width was like 3.4.
Bandwidth is not a huge priority, but we're well within that range. Basically, is what it boils down to. It's not a huge goal, but
NASA is still in between deciding if they want to count it this year or not.
yeah, they never do. They say they're gonna do it every year, they never do. But either way, we're within our bounds.
And then obviously we have the external guidelines that NASA set. They really haven't changed much. They did have in the draft something about a 4 megabits per second limit, which I think that hasn't changed from last year.
Scoring changed.
Yes, that's right. Scoring did change from last year. But like I said, that was a draft, and we don't know if that's the final limitation. They did change another thing that's very important for us. They did, on deliverables, we have to score a 70% or higher in order to go to competition, and this includes the SE paper. So that is something that changed from last year, and it's something that we have to take into account. And me and Brandon are working hard to account for that.
For reference, I think we got like 60% last year, which, I don't know, vast improvements from other years, but we just need to keep improving. With the quality of this slideshow, I'm very happy with how this is going so far compared to last year. I think we're doing pretty good. Yeah, please call out anything. Really, I think it's really important for the SE paper specifically that we have review. That is why we have these. So as we go into, like, yeah, now we're gonna go into block diagrams and like more technical details than just the backwards requirements that we've already set. Please point out anything.
I have a quick question. What does it mean that you cannot hold your autonomy mid-round?
Yeah, that's a funny story. So last year, we did that. We changed our autonomy mid-round because whenever we went to our do a dig cycle, we had actually never gotten our hands on the robot before we got down there. So we didn't know what it was going to look like. So we had to change the parameters while we were down there. So while we were in the control room, Eli changed how long the bucket went down, or basically how deep the bucket went into the ground, so that we could get more regolith into the container. They want those. They don't want us compiling code while we're in there. So our autonomy was, the parameters were hard coded or coded into it, so it needed to be compiled again. They don't want that happening again. But that's why. That is explicitly because of us.
I think we've been there before.
Yeah, that's the all true.
Any last minute comments?
I'm glad you pointed that one out there. Yeah, I put that there. Yeah, Nick, you want to explain this one?
Right here we have a pretty simplistic diagram, side view of what the robot is expected to look like this year. This is conceptual. This was meant to be rough. We'll have dimensions and upcoming slides for anyone curious. So we can see here some bigger systems to point out are, we have our bucket here. These big circles represent wheels. We have our frame base here, and then up here, the box on top is going to be the box. And we'll go into more detail about that later. So, yeah, front camera position, we expect to have that in front, towards the front of the E-box, and rear camera on the back. And then we have a new system this year, the deposition system, or the depositing robot, where we have our deposition bucket. At the top here, you can see it's a rather unique shape, pretty hard to miss. And we expect to be actuating that using a motor and bearing rails. We can talk a little more about that later as well. So we have on the left here, I guess it's right for you guys, we have a block diagram of how our system is going to connect in its entirety. So everything comes off from the frame system, go down to E-box frame, locomotion frame, and excavation frame. And then we have various subcomponents underneath those that are either structural or they are actuators, motors, our deposition bucket up here, and so on. Next slide. All right, so this is a top view of the robot that shows an overview of what's going to go where. So at the front here, we have our bucket. We are modeling after a similar shape to this bucket right here that Brandon was showing earlier. Reasoning behind that is we want to excavate at the front here a large area to dig into the ground with, and then when we raise that up, we want the regolith to pour down the bottom like a chute and into our deposition bucket up top. So we have something a little different going on with the E-boxes here. In Melody, we had that pretty large part of the frame that stuck out from the base. We expecting this to have a weight of about 2.3 kilograms or so it's a significant increase from last year. We also have, this could be easily made modular, shifted around to accommodate our changing designs and challenges for this year. So right here, you know, a lot of people had questions about how our motors work this past year and this year. Matthew here made this beautiful drawing of an exploded view of how the whole motor assembly connects. And something notable to point out is that this head shaft is screwed in to the cap of the motor that is behind it, which means that we have to disassemble the motor to get that shaft out. That's important because if you go back to the previous slide, we need to be able to get that motor out easily. So we cut some slots around the wheel hub, or the bearing hubs, where the wheels go, so that we can drop that entire assembly out really easily. 2 slides. So we use a pretty similar concept for our excavation frame and locomotion frame. This past year, using the aluminum extrusions, they get kind of heavy and they do a little more than we'd like them to. So we want to find ways to actually weight reduce those. So Ethan here on the mechanical team modeled up 2 different potential designs, one using extrusions, one using sheet metal. Find out what the factor of safety is and relative to the weights for each design. And what he found is that it's much easier to make the sheet metal variants sturdier and also lighter, using spacers in between to hold apart the sheet metal. So that's likely to be the this frame.
What material would the spacers be?
We could 3D print those. We could also cut up some aluminum tubes. We used years past, space them apart. It requires some MDA with some more rigid design.
Do you know what size screws we're using? Are we keeping that consistent across?
Yeah, we want to keep that as consistent as possible.
Yeah.
Try to keep everything the same size, hopefully, unless absolutely necessary.
Are we doing metric or imperial?
What do you think?
This is what John was thinking. You know, he did everything like imperial based on 10/32. Right? Did you say that at one point?
I wanted to go away from 10/32 and pick a common size of like a quarter.
Okay.
10/32 is a very common size.
But they're very, that's what we did last year. It didn't give us a huge fuss, but
It's essentially a 5mm bolt, which is a pretty usable size.
quarter-inch will always be cheaper. And it's really just whatever we decide we want to go with.
You can break that down depending on cost. So when we start designing components, it's going to become much more apparent once we fit with that.
Okay.
So with this new excavation and deposition system we have going on, we found a robot years past, Spacey, that the team has built. It has a very similar system. You can see here on the right, very similar bucket to this one here, and also a conveyor belt deposition system in the back. So what we'd like to change about that is we want to actuate the bucket using an actuator, because it's easier to lock to downwards or upwards. It's easier to hold a position for consistency with our excavation. Additionally, the deposition system in the back that Ben and Braden have been working on, we want to be able to tilt that backwards rather than run a conveyor belt for some more reliability, also lighter weight, less complexity, simplify things down. Over here you can see another side view of the robot. This is the kinematics of the robot. See right here we have bucket, control arm, and actuator right here. So when the actuator is fully extended, bucket is down, we're digging, fully contracted, bucket is up. We are depositing the material we collected. This is a more detailed view of the deposition system and how we intend to actuate that with the motor. So you can see here, this right here represents the motor. This is our point of rotation of the motor. That's the shaft. This is the bar connecting the motor to the deposition bucket itself. And this changing distance right here, you can see how we're at the end. And then we go further down the bucket. Excuse me. That is going to be done using a bearing rail for the mud plate so that we can slide across the bottom of the bucket and take out another link in the kinematics.
One question for the deposition. So, does the bearing, does this mean that the motor could like do a full rotation and it wouldn't hit any other part of the robot? Or is there a risk in that?
The idea behind it is we'd only be moving maybe 60 degrees with the motor. And just going from here to here. Minimal rotation.
Just, like as far as risk assessment would go, is there any risk in like what happens if
it doesn't stop?
Yeah, yeah.
That, if it does keep going, I'm not sure what the probability of that would be. The conversation to have with the electrical software. But the risk of that, we would have to look at the torque we're putting out with the motor. It's very dependent on kinematics. But yeah, if it keeps going, it doesn't stay stops and stall out, there would be a break.
Okay. Because yeah, like for the excavation system, I know we don't want the bucket to touch the wheels or like the frame or anything else. I think the same logic would apply to this. Yeah, just something to think about for next time.
Keep in mind.
Jake, another question.
Yes?
Did you guys pick 27 degrees for a particular reason?
That 27 degrees because that's just where the peak of the arm is for the length of the deposition floor.
Do you think it's going to be good enough to make sure everything slides out?
Yeah.
Something else to look at is some vibration motors, which might be beneficial to put on the bucket as well. Shake the bucket a little bit, get it out faster.
I was just wondering, what is like the rationale for using a motor over an actuator?
Actuator takes a lot of space. So it's kind of hard to get right.
What was like the decision matrix for going with like a conveyor belt versus this system?
We didn't do a decision matrix on that. It was more of a simplicity sort of deal. And how much time we have to actually make something like this, an entirely new system.
Say we need to go steeper to get all of the material to fall out, is that difficult to do with this design, or is it reasonably okay design to change how much you can tip up?
We could make it steeper. We just have to work out the kinematics for that, which they're gonna be more refined in the coming weeks.
I guess one thing with thinking of steeper, like, would that, would you have to move the motor position as well as change the length of the arm? Because changing the length of the arm, you could just like, bolt more aluminum extrusions to it. Changing the motor position, that could be tricky. I wouldn't want too many holes drilled in the box.
Yeah. Are you talking about after it's manufactured?
Yeah,
The
like let's
idea
say
is
we're testing it.
we wouldn't be making changes to the actual robot. We would probably want to test this outside the robot itself before we're drilling holes and mounting it. I think that'd be a much safer way to go about this.
Okay.
Much cleaner as well.
Maybe a question. What kind of material are you planning on using for the
freeze and turn into wax or something like that, just wax.
That's not, wax is actually not better. No, they wouldn't. We would hate that.
Yeah, some of the options we can look into. We're gonna have to come through some research papers on EP1 and LHS one as well. Roll next slide. So this year, on the left, we have potential hub design for redesign of the spoke wheels and the corrals up here. Giles, we put a lot of time to work into this, so if you'd like to come on up.
Yeah.
Talk about that.
So the basic design of the tilted grousers is to take what worked last year and just kind of improve upon it. It's really meant to improve our turning, specifically in allowing a better regolith flow, as well as just overall improvements like the overall length of the grouser. I've been doing some digging into actual NASA research papers and getting that optimal length and number of grousers. So like I just chose 5 degrees as just the arbitrary value. I guess we could change that to be bigger or smaller depending on if that's what we choose. But this is just right now the concept. And the lengths and everything, I know they're too small to actually see up here, but those are all set based on the current wheel diameter, which I believe we went with 13 for this concept. So those will also change depending on wheel diameter and the number of grousers we want to go with, because that also changes the overall angle about the grousers. This picture here is it's a concept for our improved tensioning hubs, similar to the ones on Melody wheels here, but it's focused on improving the fundamental way that we tension the whole system. So we shouldn't have to, one big design critique of Melody wheels last year was they were very, very difficult to tension. Really, there was no good way to do it. So this allows an external socket, wrench, whatever we decide we want to use for it. But there's an external way to tension on the outside of the wheel, so we're not fighting to shove our hands in between the spokes or anything like that. This also has the improved spoke attachment that Nick was working on. It allows just a better way, the top 2 up there with the kind of arcs. So instead of attaching one spoke to the rim and then the same spoke to the inner hub, it's rim to rim. So it goes all the way through the center hub from one side of the rim to the other based on whatever degree angle that is. I'm trying to shoot that is. Yes.
Do you know where on the rim or on the grouser the spokes will connect to?
That right now is something that's really just up in the air because it can go anywhere. I know at one point we were talking maybe going through the bottom of the grouser, but also we can just as easily go through the rim like how Melody is. But the big goal there is we want to get a new crimp tool so we can get that flush, good crimp. So it should theoretically be able to handle more load.
You're expecting to half the diameter of the spokes this year, since we're likely to have more of them, which makes them significantly easier to bend.
Yeah. Unless there's any other questions, I think we're good for the next slide.
So I have been looking into 3D printed wheels. A few other teams do 3D printed, and there were specifically 3 critiques that we had with Melody wheels last year that I was trying to directly combat. One of them being, yes, the manufacturability of it. It's awful trying to do the spokes in here. Like they're just sharp. It's difficult to do. So my approach to solving that problem was 3D printing, because for my whole expected assembly, it's 20 parts. There's 2 rims, 10 ground pieces, 1 hub, 2 hubs, that's kind of debatable, and then 6 pins that hold the whole thing together. And the pins have been doing phenomenal. Pins were the only thing that didn't break on this version, which I stood on to test the strength of it. And I weigh 65 kilograms, which is like close to the maximum amount of weight that the entire robot would weigh. But anyway, this just proves I'm doing a lot of testing towards this design. But anyway, 20 pieces as compared to the 120, if you count all the rivets and all the crimps and everything. That was the first problem I was trying to address. The second problem is the diameter. We wanted to increase the diameter of the wheels for sure. So having the grousers of this easily slide on and off. For testing, I could change the diameter at will. It takes an hour to print each of these, so I mean it's 10 hours, but it's also like $1/4 of a filament spool, so it's like $5. Basically, the overall manufacturing time for one of these wheels is much less, and there's much more availability to do testing of different wheel diameters. Because I don't know if like bringing it all the way up to 16 inches is good, but I know that I want it to be larger than 10. And I have the ability to switch out these browsers anywhere between 10 and 16 or more. Then the third issue I was trying to address is I think it was just manufacturing time, because it takes 18 hours to do one wheel. It's 1 hour times 10 plus 4 hours times 2. Each of these is like 4 hours, and then each of these is an hour. And then it's good. You just assemble it. It takes like 15, 20 minutes to put all the pieces together, and then you can put it on Melody and start testing it immediately. Whereas with these wheels, we had to get all the sheet metal cut at Warjet, which is like a week or 2 week process for sending that over, getting it connected back. And then it's cutting all the steel wire cables to length, machining the hubs, which is like going to the machine shop. Really good, valuable experience, but it does take a decent amount of time. It's a couple weeks. And then assembling the whole thing, it takes hours to put all the spokes together. So this was my approach to solving those problems. And there are risks in doing 3D printed wheels, because we, as a team, haven't done that before, as far as I know. The strength of it is definitely something to do more testing about if we were to do this wheel. Because obviously it's more likely to break than the metal wheel, but it's pretty close at doing the job that it needs to. And I believe I could get it there. So yeah, there's my spiel about that. I've done some FEA on it, finite element analysis, to see where any weak points are. I've mitigated most of the weak points. Before it would always break at the outer edge, but now it's like just the spokes. So yeah. Any questions about that as an option for wheels? I think it goes into, so here's a comparison, which is basically like, there were my strengths for my wheel, and then the strengths for John and Nick's wheels are definitely stronger, more reliable. It's pretty close to what we did last year. This goes into it, and then the supplemental document has a big table. This is basically the summary of that. There's pictures of everything. So we'd like to decide on which wheel to go forward with, because I don't want to waste too much more time like developing 2 different wheel sets. We're going to decide on Monday or sometime next week which one. But any comments on what people would think would be the better option of the 2?
Do we see many wheels at UCF that were 3D printed?
Yeah, the Queensland Australian team did a big 3D printed wheel, and it worked great until I think it was the first or second round of KSC where it was still UCF. I think it was the second round of UCF where it cracked.
The wheel itself.
Yeah, it cracked, and they had it all as like one print. So it took over 20 hours to do that whole new wheel. Whereas with this one, if one of the grounders breaks, that's just an hour. If one of the center things breaks, that's 4 hours. Or for this one, both of them broke at the same time, so that's 8. But still, 8 is just like an overnight thing. It'd be pretty easy to bring spares and then also just print out new ones. The whole question is just if this could last a full 30-minute run. But I would have like the 2 months of testing between now and the critical design review to make sure that it does that. And the other thing
You said it has to run 30 minutes, or we need it to run 15, 15, 30, 30. So it has to run for 2
Yeah,
hours.
so fatigue is an issue. I haven't done any testing for fatigue because I haven't put them on Melody yet. One interesting thing, these are a lot cheaper than the metal wheels, so it's the same, these are like half the price of those. So basically, if we brought 2 sets of plastic wheels, that's the same cost as bringing 1 set of metal wheels. So you could have like a full spare set and not lose any time or money. And I'm trying to design the spokes to be flexible. That's why they're so thin. Basically, I would like the wheel to deform rather than crack. Because if it deforms, then it can still drive somewhat. It'll just be like a flat tire. But if it cracks, then you really can't drive anymore. That's something I'm trying to implement for the design. And then as well as, if it can deform, then it's more likely to, like if the robot's driving at an angle, then the wheel will adjust to also be driving at that angle. You'll get more contact and more traction on the ground. That's kind of the whole point of doing a suspended hub design in the first place, where it has some suspension.
You say you're gonna make that decision come Monday, so the time of testing between today and Monday is going to be fairly limited.
Yeah, I think I'm gonna I'll put these browsers on this wheel and we'll do like 15 minutes driving on Melody if you have time this weekend. Maybe not.
Yeah, we don't have some time this weekend. I was very much under the impression that these, because we discussed having 2 wheel options in last year, and it was the metal browser ones, and then the 3D printed ones we weren't necessarily going to heavily pursue, but start prototyping this year and use them predominantly for outreach. And then if they fared well, then in years coming we would.
Yeah, I've gone back and forth on it. Right now, I would like to consider it as a competition wheel, just because it is significantly, it's like half the weight of the estimated wheel, the metal version. Half the weight's alive, and then also just the manufacturability of the machine. Like, if we have less people doing the machine work for the bending of the grousers or the making of the hub, and we have more people to put towards that new deposition system.
Brandon, how much does the metal wheel weigh, and how much does the blue wheel weigh?
This is like 1.1 or 1.2 kilograms.
Yeah.
And then this one is 0.8 kilograms.
So it's 30% lighter.
I believe where I was at in the CAD, I was at 1.7 kilograms.
For the.
That is, I have not done any optimization for weight. I have just been focusing on traction, regular flow.
But yours is bigger. Yours is the full 13 inches,
Yeah,
right?
full 13, it's the bottom left. Really, it's the weight is majorly in those, the hubs. Those were all just like numbers I picked out of the blue for a model example. So once we get further into the actual design phase, I can get a more accurate weight estimate.
Scale mine up to the 13 inches, and it's 1.1 kilograms compared to the 1.7.
Right.
Yeah. Any other questions? Those are good. Oh, yeah.
You have the ability to try printing it in nylon. It's a little bit weaker than the PET-G, but it's significantly more durable.
Yeah, that would be good. That's a whole thing too, like the material science of it. PET-G has been doing a lot better than PLA. Like the one, I left this in my car overnight, and the PLA started melting. The PET-G was fine. And the PLA will start deforming, but then the PET-G actually shatters. So maybe nylon would be more ductile, but still better than PLA. I think my printer can. I think I'm putting some of it to flush.
So where do you guys make these? Like, are you limited to only your majors labs, or do you have a separate space?
So we have a few 3D printers, like just with the design team, but I've been doing personal printers for now.
Like, I'm just curious, because like I'm in biomedical, so I have like access to my lab that has more things for 3D printing. Like, are we allowed to use stuff from there? Because I can just throw that out there that like I might have more access to more 3D printing things from the biomedical side.
100%, yeah.
And more
that'd be great.
materials, so.
Yeah, so it'd be awesome if we could use the labs.
So I can offer like that out there. If
Yeah.
we did go to the 3D route, that I know that we have more, just coming from like, because we design medical equipment, might have more to add. I think I have to get permission, but I could see it being an option.
Yeah, for sure. I mean, we should explore that if we go with this route. Another thing to consider, I have been trying to use like really easy materials to print, like PETG and PLA are decently easy, so that when we go to competition, we bring John's printer and his can print like, we want it to come out as good quality. His goes like in the back of a truck for a
But I think
while.
I could get permission to use, more materials on that side, and I know that we have more things available.
That'd be cool.
So I will throw that out there, that if we did go that route, I should
Make
have.
sure you know that. That'd be cool.
More print access and probably to nicer material.
That'd be nice, yeah.
What's your name? Kovu.
What's that?
Kovu Adams.
Nice.
So, because I know that we do kind of like fake medical devices. So, I don't know entirely what materials we have, but I always ask.
Yeah, I mean, there's good options. I've looked into different TPUs, but TPUs sometimes too flexible. And this is like, like compression is a lot of ones that were mentioned.
Because like some of the things that I know that people have done is like testing for like fake limbs and stuff, and those obviously have to be fairly light, but also hold a lot of weight. And so I don't know if any of those materials would translate to be steel, because those would be very sturdy, but they shouldn't be too heavy out there.
Yeah, that'd be good.
And they're with like long use.
Also, these are 15% infill, so, but yeah, no, that's great.
You sound very proud of your business.
I am. But yeah, because you were printing, like, you did a couple of mine, like 40% or whatever.
It's kind of like 30, 35, I think.
Okay. Yeah. I don't know, different materials, that's like the whole thing. That's, that'd be good to look into.
I can ask, well, you said you wanted to decide by Monday, but
If you ask either way, I mean,
I can ask Monday, as soon as I can ask is Monday, because that's as soon as that I can.
Sure.
Fine.
Yeah, I'll just, you know, just review it. Any other questions with that? I think that's, yeah, thank you. Good wheel discussion. Now we go to election stuff.
Let's see what you're rocking. Oh, let's see, it's what deck?
So yeah, as kind of mentioned earlier, big thing for electrical teams is trying to integrate the e-box team to the frame this year. So it's kind of been a big discussion. But along with that, we're also just working toward optimizing what worked last year, just trying to make it smaller and lighter. And so we'll lead off with Darren and what we're trying to do with PCBs for motor control this year.
So this was our PCB design last year. The name of the game is efficiency. A lot of the, not a lot, but there were some components on the PCBs that we didn't even use or we incorrectly designed. So it was just kind of extra fluff. So this year what we're moving towards is a new microcontroller that can actually connect more than just one O drive to it. So what that will do is go from 4 PCBs for every wheel O drive to 1 PCB. And also for actuators, we
we will reduce it from 2 PCBs down to 1. Along with that, we're planning to get rid of the PoE, power over Ethernet, because we never used it last year, and it would help us to use it this year. And along with that, our new microcontroller can actually talk through USB, so that's more components that we can knock off. So if you want to go to this is our new design roughly for this year. As you can see, there's no PCB. All 4 O drives would be connected to it. And actuator board would be very similar, but yeah, that's that.
And so it's in the supplemental documents. We have a decision matrix for looking at different different microcontroller options. This is particularly a brand of microcontroller I've been trying to investigate and use more. It's got a lot of features packed into it at a really low price, which is nice. Additionally, it's got like onboard PHYs for USB and Ethernet, so we can look into like further reducing components on the board. So now I'm gonna look at the box system. We'll take it over.
So our electrical box this year we're given, I believe it's a 10 by 18 inches for the size, and we're gonna have it split up into 2 shelves, one shelf for the power systems and one shelf for the PCBs. So you can see here about a good example of what we're gonna do. We haven't decided yet if the power's gonna be off the bottom of like officially, and PCB of course, whichever other one. So yeah, the shelves are gonna be removable as well. Yeah, I think that's about it. That, yeah.
Like, Chuck, and we were kind of discussing how to make the shelves be installable into the system. So had the idea of using that like edge connector, like you see on video cards, where they just slot into a motherboard. I know the team has a lot of experience in the past using that system to build a like rack of cards that all assemble together. Because without you maybe apply scaled up version. But there's also thoughts of just like if we need to just build a wire harness that connects in the back of the box to each.
This is my design for our modular battery box system. So the idea is that it's a box with kind of a pull-out shelf, you could say. So the idea would be that you have the battery arrays, which would be in their own little, you say, brackets, kind of, connected together inside of there, and then connect to the BMS. So the shelf itself, or drawer itself, I should say, will be screwed in with a gasket between the drawer and the box itself so that we can prevent as much dust as possible. And the battery terminals internally will be connected with some sort of polynickel strip or other type of conductor, probably nickel strip though, and connected. We're going to have 5 cells in parallel and then 4 sets of those in series. So we're planning to have, I believe, 100 watt hours maximum capacity and about 14 volts for the battery array. Yeah, oh yeah. So we're replacing the, sorry.
Quick question, do you know yet how the watt hours we're capable of compares to what we're expected output yet? Just out of curiosity.
I believe we're expecting 70 watt hours is what we're gonna need. So the 100 watt hours, we're actually hoping to be able to cut down our maximum power capacity so we could lighten up the amount of cells we need and the weight. But we could not find any cells that were able to produce enough power and have the right voltage.
Gotcha.
So, yeah.
Oh, have you been taking into account the change in excavation and deposition for those two? The watt hour output?
I think it should be accounted for, yes.
All right, cool.
So yeah. Another, oh, Something else we're changing this year is instead of having circuit breakers, we are gonna have automotive fuses inside, which will be a bit lighter, and though we will have to replace them if we if we pop one of the fuses. Yeah, smaller, lighter power converting. Yeah.
I don't think so. I think the idea is just we're trying to kind of optimize the system, I guess. Do you want to add your plan for the battery pack was to maybe try and move away from spot welding so it's more modular?
Yeah.
So that's part of that, if you want.
Yeah.
Slide into that.
So yeah, the idea is that if we had any issues with the batteries, instead of having them like spot welded together and you'd have to pull a bunch of stuff off to be able to replace something, instead you can simply just remove the batteries from their holders and do whatever you might need to do with the batteries themselves. So that's the hope with the modular battery system as opposed to what we had last year. So yeah, that's the goal.
Any questions?
I have a question on the microcontroller. Can you get it from a major distributor? Who did you buy it? Who are you buying it from?
I'll have to look. It's available on LCSC where we purchased components last year. It should be available through Mouse or DigiKey as well.
No, not on Mouser, not on DigiKey.
No. Okay.
Just look.
Well, we'll definitely double check that.
Yeah, so I guess this is just the one that you have used, or?
Yeah.
Okay. Because I know, 32-bit risk is probably all over the place. There's probably tons of them out there, made from very well-known companies. So.
Yeah, definitely. And there's fallback options. I know STL offers a very similar product. Although it's closer to, I think, $15 or $20 per microcontroller with the insert 4, which is kind of nice.
I think availability and maybe
Yeah.
get them. It's kind of, especially things that's only a $10 increase, is better. It's sometimes you can find a right distributor or somebody, they might just order some samples for you. But that too, so things that we're just using ones and twos, if you were going through and doing browsers and you're saying, well, we're gonna make it $10 per browser, it's cheaper, that adds up to a lot of money. But if you're using ones and twos, then $10, you wanna make sure you have plenty of boards to go through if anything happens.
Yeah, how many is it again?
We'd have like 2 covered overall system, so yeah.
Is 2 including backups?
2 on the robot. We have spares built.
Okay, gotcha. Are we planning on having one board for all 4 O drives? Would one be for the O drives and one be for the actuators?
Yes.
Oh, okay, gotcha. I was confused on where we were getting from. Thank you.
Actually, I think it's been updated since then with the deposition using a motor. That actually bumped us up to 5 O drives. But that shouldn't be an issue. No other questions?
Thank you.
Nice comic.
Hey everybody, long time no see. I'm Jackson. I'm the software manager for our team and also president can picker upper. I'm going to keep this pretty brief, just to be conscious of your time. Software is going to go over 3 main points here: the logic diagram, how we plan to optimize manual control, as well as kind of our autonomy plans. So if you could go to the next slide, please. To some of you, this might look pretty similar to what we had last year. That is because most of this is based off of last year. It is updated to involve the nodes that during development we found that we needed. as well as if you see things highlighted in purple, were not completed last year. These are what we are planning on hitting immediately this year. So while it may look like we're doing the same exact thing, we are significantly further ahead than we were last year, because again, last year's main focus was getting manual control up and running and reliable. So if you could go to the next slide. So the majority of those purple boxes and circles that you saw are related to gathering sensor information. So data acquisition is kind of the name of the game this year, seeing as manual control is pretty much already completed. This will allow us to more accurately, as a controller, understand the position of a robot, what angle we're digging at, and because we will have that data, we will have good data to tell the automation to go to. Dig at this angle, dig for this long, so on and so forth. But furthermore, autonomy and actually fleshed out autonomy isn't possible without the robot knowing where it is. Because as a observer, I can see that my bucket's so far down, so far up, so I can manually adjust for that. Without these sensors or data, the automation can't tell and cannot correct. So that is what we are hitting the ground running this year with, is that being the main focus. That being said, we will be working very closely with electrical. In fact, our meetings are at the same time, somewhat to make it easier to collaborate in that area, seeing as our data collection is dependent on the O-drive boards. So we will need to work together there. So again, that is the top priority, is getting the motor and actuator position, speed, and other data. Afterwards, we want to work towards getting data from the cameras, which Alex actually worked on a little bit last year. Man in the trenches, doing some great work out there. Anyways, so we are planning on hitting that after our sensor data, originally streaming it back, and just making sure that we have a good, solid connection so that we can begin to virtually map the environment. And now we get into a little bit more of the manual control optimization. If we are able to create a map of the area that we work in with the camera, then we can have some automatic, semi-automatic actions occur with the robot. For example, if we see that we are leaving the excavation zone, I may still be driving, but I'm not paying attention, I'm not putting my bucket up. The robot sees, hey, I'm leaving, let me raise my bucket. Where I'm entering the excavation zone, preemptively start lowering it. Stuff like that. Much like how your car can stay in its own lanes if you put it in lane check. You're still observing it, you're still in charge. If something goes down, you're there, but it just kind of helps you stay in check there. And then finally, if we get the green light on all of that, it looks like our map is accurate, it looks like our sensor data, and I cannot stress this enough, sensor data is the main thing, looks accurate and good, then we can begin to focus on or fully flesh out the dig, dump, and autonomy. Dig, dump will come pretty quickly, but the navigation autonomy, that is last step, but we should be able to hit all of that, hopefully. If you want to go to the last slide. So again, just to break autonomy down into two specific categories, we have the aided autonomy, which we talked about, and the full autonomy. Aided autonomy is our main focus for the beginning of the year. Full autonomy is what we hope to achieve by the end of the year. If we do fall short of that, we really plan on, like we did last year, building a good foundation for next year to build off of, because we have already saved insurmountable amount of time by using ROS and good coding standards to free up a lot of time for this. So the plan is to meet all of these requirements, but also make sure that next year we can just build right up on top of it. So questions, comments, concerns, quick fire, let's go. All right, really that good? All right. Oh, hey, there we go.
Yeah, you're basically, so I'm not a software guy, but you're basically using the same manual control
top.
It's on this elephant's head of it.
Exactly. That was the entire plan last year. Yeah. So, because really, moving a motor is like, stop, you're flattering me. But that was the main plan. Because Master McKay's point, a lot of those manual controls are used directly in autonomy. What we did last year was we just basically spoofed manual elements. We just did it for a certain amount of time. But it's all autonomy should do is not tell the motors to move, but tell the arm to move. The motors are handled separately. It's abstraction.
If you could go back to the data flow diagram, just like 3 back. Or it's okay, perfect.
Yeah, so you see autonomous is just by its own. Everything else, that's just a control. So that's the way we think about it. Last year, however, our autonomy was held in there, which is not exactly what we want to do. So there is some refactoring that needs to go on. But that's another thing that we're getting at the beginning of the year. So, anything else? All right.
What's the timeline looking like for, like, when do you think you'll be able to test that validity for implementing any of these new?
Good question. The sensor I want to be able to do pretty much as quickly as possible. As of right now, there isn't necessarily anything with the old PCBs that prevents the sensor collection, correct?
It's working for the wheels, the actuator board, not yet.
Okay, so that's a big thing for us. We're going to start trying to get that data pretty much within the coming weeks. Okay. But as for the final robot, again, a lot of that sensor data is dependent on the boards being manufactured, which is yeah. But we can also start on the camera stuff a little earlier. So
sensors and camera stuff, like that could probably be done by the critical design review. I'm trying to think of what kind of stuff you present.
yeah, we can probably get the sensors done by the critical. Cameras, we have them up and running, but anything useful probably not till the end of this year, beginning of next. But yeah, so that's kind of the timeline there. And then we plan for a lot of the spring to be testing. Yeah, testing and integration. All good?
What sensor are you going to use for the depositing system?
Depositing system. So that's new. I believe it uses an O-drive motor. Am I correct there? Yeah. So it's the same exact thing that we would be using for the drive motors, essentially.
But if your O-drive motor is gearboxed, how are you going to know what angle it's at any position?
So we don't actually. We can just do the math on that. Like if I know that one rotation of this is, I don't know, a fourth of rotation on that. If I rotate 4 times, it's going to go up.
Yes, but when it's at, so it's a 0 to 360 degrees, right?
Right.
The motor, not the actual, the motor versus gearbox output, the motor is 360. So when the motor is at, let's just say 90 degrees, how do you know what increment of degree your arm is at?
So you zero it. You have to zero it.
Oh, so you're going to zero
Yeah,
it.
yeah, yeah. I'm sorry. Yeah, you have to zero it.
So you're going to need limit switches.
No. You zero it and you keep track of the rotations.
So how are you going to zero it?
So zero it, you just put it into a position, and then you can put it into position, a resting position at the very beginning.
Mm-hmm.
So you could do a limit switch. There's other things that we can do for that.
I'm
you get
just-
absolute coder data or relative. Either way, I will have, you would have to zero it in manually, calibrate it and say this is my zero,
Mm-hmm.
and then it's golden from there. So it will need calibrated.
Maybe you should use a rotary potentiometer.
Nick?
What do you think the reliability on the deposition motor feedback would be? What's the chance, do you think, of it failing us, not really knowing where it's at, and just breaking a thing?
So, I'm not too worried about that.
Okay.
That being said, if it does fail, it would be pretty critical. So I do believe that we should have software and electrical aspects for just safety purposes. Not for the people with the robot.
Definitely.
Yeah, people are cheap, robots are.
Do you think it's risky enough? Do you think it's risky enough that mechanically we would need to design some sort of disconnect for the shaft?
I don't think that's a bad idea. But I'm also never going to turn down something that prevents a robot from being broken. So that is something that we can discuss further.
All right.
From a software aspect, pretty easy. We will have that no matter what. It's pretty easy for me to implement. Electrical and mechanical, while technically a little safer because if our code breaks, it breaks. Probably needs further discussion, but we can do that.
Yeah, we'll talk about that.
Yeah, we'll talk about it.
I think you can set position bounds directly in the drive controller. So that it's relatively the starting point, you have to zero it correctly. But
That's cool.
Alright. Cool. I'll let whoever's next go next. That's all we.
So we can pull up the supplementary document if you have any questions specifically about any area. We can talk about anything in further detail. This is kind of we can take a little time. Thank you guys. Thanks for coming. Thanks for listening.
I love both of you. If you guys say that one more time. Say what? You in particular. You were the real killer. Every 3 words it was of.
He's a hater.
No, I'm saying this because I actually want you guys to be better at presenting, or I don't present all.